Dear students, I am Deepak Videv, Assistant Professor, Department of Electrical and Electronics Engineering with the Academy of Science and Technology. Today's topic is wave equation for partially conducting media. So these are the topics covered in the previous lectures of this module. We covered wave equation for free space and perfect dielectric, and also the derivation for intrinsic impedance for perfect dielectric and free space. In the today's lecture, we will be covering the wave equation for partially conducting media and the intrinsic impedance for partially conducting medium. Okay, this derivation is also similar to that of the wave equation for free space or for lossless dielectric. But here there is a small change. So if you want to know that change, you have to know what does mean a partially conducting medium. What is partially conducting medium? It is also known as a lossy dielectric. We know that in all dielectric are not pure. There may be some amount of conduction loss in any dielectric. Such dielectric having small amount of conduction loss or conductivity are known as partially conducting medium or lossy dielectric. So in this material, they are not pure dielectric. They have some amount of conduction loss. Conduction loss means I square R loss. That's why in such medium, J will not be 0. In pure dielectric, conduction current is not there. So J is 0. But in case of lossy dielectric or in partially conducting medium, J not is equal to 0. In this medium also the volume charge density is 0. So it is similar to dielectric in case of volume charge density, because all of the charges may be on the surface. Inside that material there won't be any charge. So conduction current is not 0, but the volume charge density is 0. So we will apply this condition into Maxwell's equation, and we will obtain four equations as shown here. The first equation comes from Gauss law for electric field. That is, we know that it is actually del dot D is equal to rho V. Here rho V is equal to 0. So del dot D becomes equal to 0. For D we can substitute epsilon 0 epsilon R E. So it becomes del dot E is equal to 0. Thus we obtain the equation 52. Then there is a Gauss law for magnetic field, that is del dot B is equal to 0. So we will substitute B is equal to mu 0 mu R H. From that we will obtain del dot H is equal to 0. So del dot E is equal to 0, del dot H is equal to 0. Then we have the Faraday's law, del cross E is equal to minus dou B by dou T. For B we can substitute mu 0 mu R H. So it becomes del cross E is equal to minus mu 0 mu R dou H by dou T. Then we have modified Ambier's law, del cross H is equal to J plus dou D by dou T. So we will substitute D equal to epsilon 0 epsilon R E. So it becomes equation 55. That is del cross H is equal to sigma E plus epsilon 0 epsilon R dou E by dou T. Here J is equal to sigma E. It is the continuity equation that we already derived. So we modified the Maxwell's equation. So here one of the important difference is we have a J. So J we can substitute as sigma E. It is the continuity equation. So the Maxwell's equations for partially conducting medium become del dot E is equal to 0, del dot H is equal to 0, and del cross E is equal to minus mu 0 mu R dou H by dou T, and del cross H is equal to sigma E plus epsilon 0 epsilon R dou E by dou T. Okay, now let us take curl on both sides of equation 54. This is the same step that we used in the previous derivations. So from the equation 54 we are taking curl on both sides of the equation 54, so we will get curl of E is equal to curl of minus mu 0 mu r dou h by dou t. Now we have the mathematical identity which says that curl of E, curl of E, this term is equal to gradient of del dot E minus del square E. It is a mathematical equation, mathematical identity. Okay. Then in the right side, we will be there is curl of minus mu 0 mu r dou h by dou t. We will take that curl inside and we will obtain this term. Okay, and here del dot e is 0. That is in the previous slide. Del dot e is equal to 0. It is from the Gauss law. And here curl of h, del cross h is equal to sigma e plus epsilon 0 epsilon r dou e by dou t. It is in the previous side and it is obtained from the Ampere's law. Okay, so this equation becomes here this one, that is del square e is equal to mu 0 mu r dou by dou t of sigma e plus epsilon 0 epsilon r dou e by dou t. Then taking the constants inside the equation, we will obtain the equation 57. This equation 57 represents the wave equation for electric field. Thus we have the wave equation for partially conducting medium as equation 58. Equation 58 represents the wave equation in terms of electric field. As in the previous derivation, we can use the same steps. We can take the curl on both sides of equation 55 and we may follow these steps. We will obtain the wave equation for magnetic field as equation 59. Both of this equation 58 and 59 have the same form. In 58 we are using the vector as electric field vector, and equation 59 it is the magnetic field vector. So both equations are derived in the same manner. These both equations represents the wave equations in case of partially conducting medium. So what is the difference of this equation from that of a dielectric material? There is an extra term. What is that extra term? This one is the extra term in the partially conducting medium. The reason for having this term is the presence of sigma or J. Sigma represents the conductivity of the medium. So this term is responsible for the dissipation of power in the medium. So if the wave is propagating through a partially conducting medium, there is a dissipation of power, and this term is responsible for that dissipation or loss of that power. Okay, so if the term sigma is dominating in this equation, then that wave do not advance much into that medium. That we can infer from this equation, these two equations. That is the inference from these two equations. These two equations are in the differential form. When it comes to partially conducting medium, these two equations does not reveals much more about the power dissipation in the medium. But if we can convert it into phasor form, this will give much more idea about the power dissipation. So we will try to represent this equation in the phasor form. That form is very simple to obtain. So here, for obtaining the wave equation in phasor form, we will represent the Maxwell's equation in the phasor form. It is very simple. You have to substitute d by dt or dou by dou t term by j omega. Then you will get Maxwell's equation in the phasor form. So we have these are the previous Maxwell's equation. If you substitute this term. Here there is a dou by dou t term. So instead of dou by dou t, if you substitute j omega, you will obtain these equations in the phasor form. That is shown here. Here del dot E is equal to 0. It is similar to here. Del dot E is equal to 0, del dot H is equal to 0. The first two equations are same, but equation 54 you can write as del cross E is equal to minus j omega B. Actually it is minus dou by dou t of B. Instead of dou by dou t, we will be substituted it by using the frequency term j omega B. So and B is equal to mu 0 mu r h. So equation becomes del cross E is equal to minus j omega mu 0 mu r into mu 0 mu r into h. Next, del cross h. Del cross h is equal to actually j plus dou d by dou t. So we will substitute dou by dou t as j omega. So it becomes j plus j omega into d. Then as in the previous case, instead of j you can substitute as sigma e. It is the continuity equation, and you can substitute d as epsilon 0 epsilon r e. Then we can take electric field outside and it becomes equation 63. Thus the equation 60-63 represents the Maxwell's equation in phasor form for partially conducting media. Now for obtaining the wave equation, we will follow the similar step as in the previous derivation. First we have to take curl on both sides of this equation. Then it becomes curl of E is equal to minus j omega mu 0 mu r curl of h. You can substitute curl of h as sigma E plus j omega epsilon 0 epsilon r e, and it becomes this term. Okay, then in the left side the curl of E can be substituted as substitute as gradient of del dot E minus del square E. It is the mathematical identity. In equation 65, del dot E is equal to 0. It is in the previous slide. Del dot E is equal to 0, and it becomes minus del square E is equal to minus j omega mu 0 mu r into sigma plus j omega epsilon 0 epsilon r into E, and you can substitute this term. Both minus will be cancelled, and this term, this complex quantity, can be represented by a letter omega square. So the equation 65 becomes del square E is equal to omega square E, where omega is known as propagation constant. It is equal to root of j omega mu 0 mu r into sigma plus j omega epsilon 0 epsilon r. It comes directly from here, directly from this term. Okay, so omega is known as propagation constant, and we can represent it as omega is equal to alpha plus j beta. Omega is a complex term, so it has a real part. That real part is termed as alpha, and the imaginary part is termed as beta. Alpha is known as attenuation constant, and beta is the phase constant. So if you know the value of alpha and beta, we can infer much more details about the wave propagation in that media. And the alpha is known as attenuation constant. It represents the amount of attenuation that take place to the wave in that medium. That's why it is known as attenuation constant, and beta is known as phase constant, as it represents the phase shift of the wave. So propagation constant is a complex quantity, and its real part is alpha and the imaginary part is beta. Real part is known as attenuation constant, and the imaginary part is known as phase constant. By knowing the value of beta, we can find the wave velocity directly by using the formula 69, that is omega by beta, where omega is the 2 pi f. F is the frequency of the wave. So omega by beta, and the wavelength lambda is obtained by 2 pi by beta. Okay, so now let us derive an equation for finding the value of alpha and beta. So we know that gamma square is equal to j omega mu 0 mu r sigma plus j omega epsilon 0 epsilon r, and gamma is equal to alpha plus j beta. So we can write it as alpha plus j beta whole square, which will be alpha square minus beta square plus 2 plus j into 2 alpha beta, and the right side become this term. And we can equate the real part here. This term is the real and this term is the real, and so we can equate that real terms and the imaginary terms. These two terms can be equated. So we obtain two equations. These two equations are non-linear equation. This term is non-linear and this is linear. So both equations are non-linear, and you can solve that non-linear equations and you can find the equation for finding the value of alpha and beta as these two equations, alpha and beta. These equations are used for finding alpha and beta in a partially conducting medium. By knowing their values, we can get more idea about the wave propagation in the medium. That is the importance of these two equations. Okay, so in this lecture we derived the wave equation for partially conducting media, both in differential form and in the phasor form, and derivation for attenuation constant and beta phase constant is also done, and the gamma is the propagation constant. Okay, I hope all of you understood about this topic. Thank you.